So we are finally in a position to consider the one-dimensional central limit problem. So let me remind you what the problem is. So we have an array, x and j, of independent random variables, j from 1 to kn, kn converging to plus infinity, and we wish to find sufficient conditions in order that the sum of x and j minus a certain real number an, a sequence of real numbers, converge in distribution to some limit. And what we proved so far is that in order to prove this result, it's sufficient and also necessary to consider the limit of the sequence y tilde nj minus an prime, so a new sequence an prime. And, well, the distribution, the characteristic function of this new random variable, so let me make it clear. If we want to prove that this sequence converge in distribution to S, it's necessary and sufficient to prove that this sequence converge to S. And in order to prove that this sequence converge to S, well, what we have to show is that consider the characteristic function of this random variable and to prove that this sequence of characteristic functions converge to a function which is equal to 1 at 0 and which is continuous at 0. Well, but this characteristic function, we know its value. It's given by the exponential of the integral of the exponential of I tx minus 1 minus I t theta x dmn plus I t an, where an is related to an prime, and where theta x, it's a function which is essentially x close to the origin, and it's continuous and bounded. So theta x, it's a continuous bounded function on R, and we impose the bound that theta x minus x, it's bounded by a constant times x cubed for x less or equal than 1. So that there exists a finite constant c such that this difference is bounded by constant times x cubed if x is less or equal than 1. So if we want to prove that this sequence converge, we have to show that these characteristic function converge, and remind that mn of the x is just the sum of mu n j dx in j, where mu n j is the distribution measure of the random variable x and j. So if we want to prove that this limit holds, we have to show that this sequence of characteristic functions converge, and what we want to establish are necessary and sufficient conditions for this to happen. And this is the main theorem of this lecture. So let me try to state it here. So the theorem says the following. Well, assume that the following three conditions holds. The first one is that for all functions f which are continuous and bounded, so CBR means that the function is continuous and bounded, and such that there exists a delta which is strictly positive, such that f of x it's equal to 0 for x less or equal than delta. So I'm assuming that for all continuous bounded functions which vanish in the neighborhood of the origin, the following holds. Well, fx dmn converge to fx dm. So I'm assuming that there exists a Levy measure M, a constant sigma square less or equal than, well, non-negative sigma square, and a constant A, such that the following three conditions hold. The first one is that for all f, which it's continuous and bounded and vanish in the neighborhood of the origin, we have this convergence. The second condition say that, well, there exists x0, which is a continuity point, or x0 positive, which is a continuity point of M, the Levy measure M. This means that the measure of the point x0 plus the measure of the point minus x0, so here we require x0 to be a continuity point, but also minus x0 to be a continuity point. So assume that the measure of these 2 points is equal to 0 for the limiting measure. And we require that the integral from minus x0 up to x0 of x squared dmn. So this is well defined because mn, it's a Levy measure. That this plus sigma n squared divided by 2, assume that this converge to minus x0 up to x0 x squared dm plus sigma squared divided by 2. So the second condition requires the existence of a point x0 for which this sequence converge to that one. And finally, let me write maybe the third condition here. The third condition concerns the sequence an, which appears here. So the third condition states that an converge to A. So let me read again the assumptions of the theorem. I'm assuming that there exists a Levy measure M, a non-negative constant sigma square, a real number A, for which these three conditions hold. Then the theorem states that, well, if I consider a random variable x, which has the distribution associated to mn, sigma n squared, and an. So remember, this is saying that x has an infinite divisible law, which has parameters mn, sigma n squared, an. Then this sequence of random variables converge to, in distribution, to a law, which is the law associated to m sigma square A. So we have seen, we introduced in the previous lecture a family of distributions. So we associated to each Levy measure m non-negative constant sigma square and real number A, a distribution. And what this theorem is saying is that, well, if these three conditions are satisfied, then this distribution converges to that one. Note that here, this distribution, it's exactly corresponds to the distribution x mn 0 an. Right? The distribution of the sequence sum of y tilde nj minus an can be represented by one mn, one Levy measure mn, and constant an. So we have here sufficient conditions which guarantee that this sequence, therefore that this sequence of random variables converge in distribution to a known distribution. So the distribution which is associated to the Levy measure m, to the constant sigma square, and the constant A, to this triple. Therefore, here, this theorem completes the solution of the central limit problem. We have sufficient conditions which guarantee the convergence of this sequence, and therefore the convergence of this sequence. And what's remarkable about this theorem is that, well, these conditions are not only sufficient, but they are also necessary. So let me state here the Converse theorem. So the converse states the following. Well, assume that you have this sequence. So we have a sequence of Levy measures Mn, a sequence sigma n square of non-negative real number, and a sequence of real number an. And assume that the distribution associated to this triple converge to some law. So assume that this sequence converges in distribution to some law. Then what I claim is that there exists a Levy measure M, there exists a non-negative real number sigma squared, there is a real number A, such that the distribution of X is equal to the distribution associated to M sigma square A, and one, two, and three are satisfied. So these conditions are not only sufficient for the convergence, but they are also necessary, because if this sequence converges in distribution to some law, then this law, there exists a triple M sigma square A, such that this law is the law corresponding to this triple, and moreover, conditions 1, 2, and 3 are satisfied. So the lecture today will be concentrated on the proof of this theorem. We will start by proving the converse, and then we'll go to the first statement. So actually, I said it wrong. What I will prove is that, first I will prove that if you have a sequence of Levy measures Mn, the sequence sigma n square, and sequence an, if there exists a Levy measure M or a triple M sigma square A, such that these three conditions are satisfied, then we have convergence in distribution of a random variable which has this distribution to a random variable which has this distribution. So there is a convergence of this law to that law in distribution. And so mind the notation. Here I'm representing, if I have a Levy measure M, a non-negative constant sigma square, and a real number A, X M sigma square A represent a random variable whose distribution is characterized by these three parameters. And this has been introduced in the previous lecture, and in the previous lecture we have shown that these parameters are uniquely defined, provided that the measure M, which is a Levy measure, puts weight 0 at the point 0. So this is the notation. So I want to prove this statement, and in order to prove that statement, I will start with an observation. The observation is the following. Well, if this happens for one x0, then which has this property, then it happens for all x which share this property. So let me take x1, such that the measure of x1 plus the measure of minus x1, it's equal to 0 for the limit measure M. And what I want to prove is that, well, this limit converge for replacing x0 by x1. So let me consider x1 minus x1 plus x1, x squared dmn plus sigma n squared. Let me assume, without loss of generality, that x1 is larger than x0. You see that the same proof applies in the other case. So the idea here is, of course, to write this as minus x0, x squared dmn plus sigma n squared. And then we have two pieces which remain, the pieces from x0 to to x1 and the one from minus x0 to minus x1 to minus x0. So let me consider just one of them. What I claim is that x0, x1, x squared dmn converge to x0, x1, x0 dm. So here I have two terms, in1 plus in2. in1 is this term, in2 is the other one which goes from minus x1 to minus x0. This expression here converge by assumption to minus x0, x0, x squared dm plus sigma squared. So it remains to show that this expression converges to that one, and the same thing for minus x1 and for the integral from minus x1 to minus x0. So let me prove this one, and the other one it's identical. So in order to conclude the proof of this observation, I just need to show that this limit holds. And therefore here, so let's prove that. Here we have x0, here we have x1, and here's the function x squared between these 2 points. So what I will do is I will define two functions. One function which it's continuous. So let's say that here's here's 0. I'll consider two functions which satisfy this first property in order to prove that limit. So the first one will be this function. So let me take a delta. So this is the point x1 plus delta, and this is the point x0 minus delta. Let me take delta sufficiently small for x0 minus delta to be strictly positive. And this is a function which I will call f delta. So f delta, it's a continuous function. It's equal to x squared between x0 and x1, and it vanishes from x1 plus delta to plus infinity, and the same thing from x0 to minus infinity to x0 minus delta, and say it's linear between x1 plus delta, and x0 minus delta, x0. So this is the function f delta. So it's clear that, so in order to prove this, we'll get a lower bound and upper bound. So for the upper bound, we will just say that x1, x0, x1, x squared dmn, it's less or equal than this function f delta dmn, because x squared, it's bounded by f delta, and mn, it's a non-negative measure. Now I can use 1 to say that as, because f delta, it's continuous bounded, and it's equal to 0 in the neighborhood of 0. So I can send n to infinity to say that this converges to f delta of dm. And now I can send delta to 0. So this holds for all delta. Now I can send delta to 0 to say that because x0 and x1 are continuity points of M, that as delta converges to 0, this expression will converge to the integral from x0 to x1 of x squared dm. So I leave it to you to check that if x0 and x1 are continuity points, then as delta goes to 0, this integral converges to that one. So this provides you an upper bound, and we get the lower bound in a similar fashion, but now instead of taking f delta, we will take g delta, where g delta will be a function which is defined similarly, but now we want a function which is bounded by x squared. So that will be x0 plus delta, and this point will be x1 minus delta. The function will be linear in these two intervals, and it will be equal to x squared in the remaining part. So by defining this function as a function g delta, we can repeat exactly the same argument and get a lower bound for this limit, and that would prove this statement, and therefore that there's nothing particular from this point x0 if this condition 2 holds for one continuity point. By continuity point, I mean that x0 and minus x0 are continuity point, then it holds for all continuity points. Now, let's start the proof of this theorem. So in order to prove this theorem, what we have to show is that the characteristic function associated to the triple mn sigma n square an of t converge to the characteristic function associated to the triple m sigma square a t, and that this limit holds for all t in R. Now, if you remember, the characteristic function associated to this triple mn sigma n square an, it's given by the exponential of the integral of exponential I tx minus 1 minus I t theta x dmn plus, or let me write minus sigma n square t square over 2 plus I t theta n. And so this is the characteristic function associated to this triple. Therefore, if you want to prove this convergence, what we need to show is that the expression inside the curly braces converge to the same expression in which I replace mn sigma n and an by m sigma and a. So what we need to prove is that for all t, this expression converge. Of course, if I use, so I will do that in 2 steps. There is a 0 step, say, which is obvious, is that since an converge to a, well, this piece here converge. So this one, I don't need to take care of it. And what I really need to show is that this expression converge to the same expression with mn and sigma n replaced by m and sigma square. So let me write it as a difference. And to save time, I won't write the expression. And what I will do is that I will fix a continuity point x0 of m. By continuity point, I mean a point which satisfies this condition. And since m, it's a finite measure, if I remove an interval, a small interval around the origin, you see that there are at most a countable number of points in which the function m is discontinuous. So number of points in which there is a positive mass at x is countable. So I certainly can find a sequence, the sequence which decrease to sequence of point, which decrease to 0 and which satisfy this condition. So I avoid this superscript. I'll just pick a point x0 which satisfies this condition, and at the end, this point will converge to 0. So I will divide this difference in 2 pieces. The first one, I will use that condition. So note that this function here, it's a function which is bounded and continuous outside of the origin, right? So if I fix x, I consider x larger than x0, and the function itx minus 1 minus I t theta x dmn, and I compare that to the same expression, what I claim is that for all x0 which satisfy this condition, this converge to 0 as n goes to infinity. And, well, there is a problem, of course, at x0, because what we are doing is that this function, it's a bounded and continuous function. So let me consider the interval x0 to infinity. The same argument will apply to minus infinity minus x0. So here we have a bounded function, because theta x, it's a bounded function, it's continuous. So this is a bounded continuous function, and it has a certain value at x0. So here is the function, and what we are doing here is that we are cutting this function by placing this indicator of this set, is that we are setting this function to be 0 at between minus x0 and plus x0. So that, of course, we can't apply directly this condition in order to say that this converges to that expression, because there is a discontinuity at this point. But now we can repeat the argument I just presented before by replacing this function by a function which is continuous and vanish at the left of x0 minus delta, and another function. So this function, it's bounded. The first one bounds our function. The second one, it's bounded by our function. Now we can apply this result for these two functions. So this one I was calling f delta, and that one I was calling g delta. So we can replace this function by f delta first. Of course, there is a price, but this price, it's the difference between, so this function here, it's bounded. So we can estimate, so let me call this function f. And what I'm doing is that I'm replacing, so let me write it here to give you all details, though it's quite simple. So what we are taking, it's a function f, which unfortunately it's not continuous at x0. And we are replacing by f delta of x dmn. And I'm taking f delta dmn. So what I know is that for all delta, this expression converges to f delta dm. And since x0 is a continuity point of m, that this expression converges to f dm as delta goes to 0. Now I have to say that this expression here, it's bounded. Well, but I can bound it by, so f minus f delta, it's bounded by a constant. So this is in absolute value, it's bounded by a constant times the indicator of an interval x0 minus delta x0 dmn. Now, if you wish, I can again replace that by a continuous function which is 1 in this interval. I can send that to now n to infinity to say that this converges to h delta dm. And now I can send delta to 0 to claim that this converges to 0 because x0, it's a continuity point of m. So, well, this is clear. F minus f delta, it's bounded because the difference, they differ only in this interval. And in this interval, the difference, it's bounded by the value of f at x0. So that's clear. Now I'm just comparing a function which is 1 in an interval by a function which is continuous. And, well, linear in some small interval. So this is the definition of h delta. Now h delta satisfies the conditions 1, so I can send n to infinity to get this limit. And finally, I can send delta to 0 and use the fact that x0 is a continuity point of m to say that in this limit goes to 0 as delta goes to 0. So that's proof that indeed this integral converge to the same expression with mn replaced by m as n goes to infinity. So this is the first claim. The first claim is that for all x0, which are continuity point of m in this sense, this difference converges to 0. So what I have to estimate is the opposite, x less or equal than x0. But I have this extra term, which is minus sigma n square tx square divided by 2. So what remains to be shown is that this difference converges to 0 as n goes to infinity. And here, as I said, I will use that, I will take smaller and smaller x0 in order to prove that. So, well, the second condition here will be used in order to prove that. So what I will do is to rewrite this difference as x smaller than x0 exponential I tx minus 1 minus I t theta x minus, in the sense that plus sigma square t2 divided by 2 dmn. And then since I added this term to this integral, I'll take it out. So minus x squared. Let me place t square outside. Sigma square divided by 2 dmn. And I have here minus, so let me put minus t square divided by 2 x smaller than x0 plus sigma n square and minus the expression. So from this line to this line, the only thing I did is to introduce inside the integral x squared t squared divided by 2, and I removed it in the second term. And of course, since I have sigma n squared t2, I put them together. Now, from condition 2, I have that the second term converge for all continuity point x0, but x0 is a continuity point. So for all x0, this term converges to 0. The difference of these two terms converge to 0. So what remains to be estimated is the difference of this one with the same expression with mn replaced by m. So it's this difference which has to be estimated. And well, this difference, what we will do is to show that actually each term is small, provided x0 is small. So let me bound this difference by the absolute value of the first one plus the absolute value of the second one. Let me concentrate it on the first. The second is estimated in the same way. And here, well, what we will say is that I will use here the property of theta x. So we never used, and this is where we are going to use, that theta x minus x, it's bounded by constant x to the cube. So what we will do is, well, we have the expansion of exponential I tx minus 1 minus I tx plus x squared t2 divided by 2. And I introduced itx. So let me minus itx. So let me take it out. So I have plus itx minus theta x dmn. Let me assume that x0 it's bounded by 1. So I can use this estimate. Now, here I have the Taylor expansion of exponential itx. And so we know since all derivatives of this function are bounded, that this is bounded for x smaller than x0. So since x0 is bounded by 1, there is universal constant C1 for which the absolute value of this expression is bounded by x cubed. And for the same reason, by this assumption, we know that this expression is bounded by x cubed. And here I'm allowing the constant C1 to depend on t because t is fixed. What we need to prove is that this holds for all t, but t is fixed, so I don't care about that. And so the conclusion is that the absolute value of this integral, it's bounded by a constant which depends on t of x smaller than x0, x cubed dmn. Now that's perfect because I can estimate this expression by constant ct. Remember that x0 it's positive, and this is bounded by x less or equal than x0, x squared dmn. Right, because x is bounded by x0, so I took x0 out. Now, of course, I can add here sigma n squared and use that x squared plus sigma n squared. It's converging. So this is as n goes to infinity. It's converging to ct x0, the same expression. With m instead of mn and sigma instead of sigma n. Now we are in business because m it's a living measure, therefore this integral is finite, sigma it's a real number, so that's finite, so this converge to 0 as x0 converge to 0. So we divide our expression in two terms, one which was converging for all x0 fixed, and the second one which converged to 0 as n goes to infinity and then x0 goes to 0. So by putting them together, we reach the conclusion that indeed this characteristic function converges to that characteristic function for all t, and therefore that this sequence of law converge in distribution to this law. So that completes the proof of one statement of the theorem, which is the simpler one. And now let's move to the other one, which is more demanding. So before we go to the converse, let me just remind that in the previous proof, when I sent x0 to 0, I was always considering points of continuity points of m. So all these points were points such that minus x0 it's equal to 0. Right? But since there are most countable number of points such that mx mx it's positive, because m it's a living measure, there is a most countable number of points x such that this happens, we can find a sequence of points converging to 0 which satisfies this property. So maybe I didn't insist enough on that point. And a second comment is that, well, once we prove this theorem, now we have sufficient conditions to guarantee that our sequence x n j minus a n converge. Right? Well, from this sequence of distributions, we construct mn. Mn, it's the sum of the distribution measures associated to the random variables mn. And the problem is reduced in finding a sequence an. So an is associated to that sequence. such that the distribution, well, the triple mn0 an, so we have to look for a sequence an such that the triple mn0 an satisfy these conditions. So is there a sequence an for which there exists m sigma square a such that these three conditions are satisfied? So that provides an answer to the problem we raised a few lectures ago. And what we are going to show now is actually that these sufficient conditions for the convergence are actually necessary. So we are not imposing anything too strong because, well, this statement tells us that these conditions are also necessary and are not only sufficient.